we go. Got to get permission for these sorts of things. Right, well, first of all, apologize for this croak that's coming out. It's nothing to do with the microphone, it's just me. Okay, well, we got a bit of a sort of a Cretaceous into Paleogene theme going for this lecture and the next one. Rory Mortimer and his compadre Danny Long will be here to talk about their Cretaceous chapter for Geology of Scotland in 2 weeks' time. But tonight we've got Uisdean Nicholson from Heriot Watt, and going to be talking about, I suppose, a serendipitous discovery in seismic offshore West Africa. And I'll leave Uisdean to talk about those discoveries in a moment. Uisdean was an undergraduate at Glasgow, and then he went to my stamping ground in Aberdeen. And we were sharing over a meal names that we knew in common, like Alan Crane and Gordon Walkden, Nigel Troon and so on, Clive Rice. And so a shared generation. I was there much earlier than Uisdean was, but a shared generation nevertheless. And then from Aberdeen, off into the world of work and experience, amongst other places, Shell. And then, about 6, 7 years ago, came back to Heriot Watt and worked with the group there, and working to establish a research group in seismic working, seismic determination, seismic research, and looking at the vast wealth of data that is available from lots and lots of commercial activity, and making their data sets available in due course or as the work proceeds. So there is a wealth of data out there, and it's one of those blocks of data that Uisdean's going to be talking to us tonight from the, I've got to stop thinking of it as a KT boundary, because it's got to be the Cretaceous-Paleogene boundary these days. I'm not allowed to say tertiary anymore, but there you go. Anyway, Uisdean, thank you.
Thank you. Can you hear me all right? Is the microphone working? Yep. Great to see some familiar faces in the audience. Some nice surprises there. So, and thanks for inviting me to come tonight and share some of the recent research that we've been doing at Heriot Watt, but also some other research partners across the world. So I've got 2 titles tonight. One of them is a little bit misleading, and it's this first one. So this is a headline from, I can't remember what media article this was, but after the paper that we published, on which I'm going to be talking tonight, was published last year. It was covered quite extensively in the press. This is one of the headlines. I could have put some other similar ones. So not 1, but 2 asteroids might have slain the dinosaurs. I guess most of you in the room are familiar with the idea, the theory that the extinction of the dinosaurs and many other creatures, or the non-avian dinosaurs, I should say, and many other organisms at the end of the Cretaceous period occurred because of a large asteroid impact, the Chicxulub crater in Mexico. That's pretty well established. It's pretty robustly constrained now, so we think that's almost certainly the case. But I'm going to give you a slightly more nuanced title for the talk tonight, which I think was on the advert, I presume, is the Nadir Crater, a new candidate Cretaceous-Paleogene, KPG, impact structure. So the other people on here are some of my co-authors. So my PhD student, Ben, did some of the seismic, tied some of the seismic to the biostratigraphy to help with the age model, and then a couple of co-authors from the United States who help with the modeling and interpretation. So the way I'm going to do this tonight, I'm going to give you a little bit of an introduction to impact cratering, because I guess not everyone will have a lot of in-depth knowledge on this. I'll then introduce you in the second part to the crater, or the proposed crater, and provide some evidence for an impact origin for this, why I think this is not just a volcanic crater, for example. Then I'm going to go through and think about some of the environmental consequences of such an impact, this specific impact and this kind of impact in general. And then the question that caught at least a lot of the public attention is the proposed relationship to Chicxulub, to this big asteroid that led to the extinction of the dinosaurs. And then I'll close out just with some to highlight some things that are still ongoing in this project, things that we hope to do in the future, including to take a drill ship and go and drill down into the crater below 300 meters of sediment and 900 meters of water. So look out for that in future. First of all, a brief introduction to impact cratering. So we're looking at craters on Earth or on rocky planets or on icy moons in the solar system. You generally classify them according to whether they're simple craters or complex craters. And there's a cross-section of each shown on the bottom of the page on the left-hand side, and a map view on the right-hand side. So simple craters are, very much what you get if you throw, firmly throw a rock into soft sand or mud or something like that. You get a concave up circular geometry with a raised rim, so an elevated rim, which is partly caused by material that's thrust underneath, laterally underneath the surface, and also partly by the presence of this ejecta blanket. That's material that's been thrown out of the crater and cascades down or is deposited on the flanks of the crater. In the case of a complex crater, you have many of the same elements, but there's a key difference here, and that's the presence of this feature here, the so-called central uplift or the stratigraphic uplift. You can see it here. You can see the very surface expression of that here, the central uplift, and then here what it looks like in the subsurface. So this is inferred. This has, of course, never been observed in real life, but it's inferred to occur because of a process called acoustic fluidization. So the reverberations, the energy involved in the impact, causes these intense reverberations in the subsurface that lead to the grains in sediments, for example, or even crystalline rocks, the mineral boundaries being separated, and the material flows like a kind of ductile fluid back up into the transient crater. So this is very much this is very characteristic of these larger craters. So on Earth, the boundary, the threshold between these two is about 3 kilometers. It's slightly different if you're on the moon, for example. The threshold is slightly larger because gravity has less of an effect. One other thing to point out is these terraces. You can see in the complex crater, outside of that, you don't just have a simple rim, but you also have these terraces that form as the material collapses into the transient crater. So that is the key distinction. And what I'm going to be looking at, or going to show you, or I'm going to hope to convince you, is that we have a new complex crater offshore West Africa. Just a little bit of context, historic context, and then context going further back in geological time. The largest, there has never been in recorded history of the last few thousand years, there has never been an impact, an asteroid that got through the atmosphere and made a crater at the Earth's surface. So the closest thing to that was the Tunguska event in 1908, so a little over 100 years ago. This Tunguska is in East Siberia. The photograph on the top there shows a picture taken at the time. It was very enigmatic at the time. There was a loud blast, there was a loud explosion. When people went to investigate the scene, there was an area of about 2,000 square kilometers of forest that was flattened. But what happened there, according to the latest research, is that there was a 50-meter asteroid, approximately, somewhere between 25 and 75 meters, that exploded several kilometers above the Earth's surface, a so-called air blast. And it was the air blast that flattened the forest. So the asteroid itself never made it to the surface. Another event that many of you will remember, is Chelyabinsk. It's only 10 years old, so there's nobody in this audience I guess there's nobody in the audience who is old enough to remember this one, but there is to remember Chelyabinsk. That was only 10 years ago, and it was little video clip of it here. There were lots of video clips of this event. windows exploding, the sound of the air blast as it exploded. So again, this exploded some, I don't know, a couple of kilometers again above the Earth's surface, and it was a 0.5 megaton explosion compared to a 12 megaton explosion for Tunguska. In order for an asteroid to be large enough to pass through the atmosphere without fracturing and exploding, it really needs to be larger than 50 to 100 meters. And there are no documented examples of anything like that in Earth history. So to understand what that might look like, you have to go further back in time. This is a figure showing, this is just a picture taken from the website of the Impact Earth, is the database and the website. And that shows you the surface location in the orange kind of fireballs of the 200 documented craters on Earth. So they're documented in that somebody has gone to the crater and recovered samples and found evidence of shock metamorphism, extremely high pressure metamorphism that's affected the shock quartz grains in particular, but other minerals as well. That shock metamorphism you can't replicate by any other process. So it's the diagnostic criteria for an impact event. You can also, so Chicxulub is highlighted there. There's the one that led to the demise of the dinosaurs. As well on here are a number of impact deposits. So the little kind of blue clouds, I don't know what they're supposed to represent actually, but these are the impact deposits that are in this database. So again, these are sedimentary deposits with shocked minerals entrained within it. The closest one to us, well, there are two in the north of Scotland. One is the Stackfata member. There's the Northwest Highland field guide here documents it, if you're interested. I went there in the spring, and it's an amazing feature, kind of a sand slurry with volcanic glass within it and huge boulders sitting below it that have been ballistically ejected from a crater somewhere and embedded in the sediments at the time. Kind of curiously, there are only 20 of these craters, and well, excluding the ejecta layers, the impact deposits, there are only 20 of these craters that are marine target craters. That is, craters that landed in the sea. So this is a bit peculiar in a way because the Earth's surface is 71% water. So we would expect 71% of the impacts to be on water. Some smaller ones wouldn't make it through the water column, and so the crater would form in the sea, not in the seabed. But anything larger than a half a kilometer or so should leave a crater behind. So that's the first curiosity. Only 20 marine target craters. And of course, the other couple of factors here. One is that we just don't have. You can't go and look at so easily at the seabed, right? We understand less about the seabed than we do the surface of Mars, for example. So there's lots of, there's probably quite a lot of craters out there in the sea, but we haven't seen them. We had to have the data to document them. If we look at crater, the other factor is preservation in the ocean. So the ocean crust, of course, is consumed every 200 to 300 million years by plate tectonics. So the record doesn't go as far back in time. That's part of the reason why we have this distribution here. So on this chart, we see age on the y-axis, going back to the Proterozoic, and we have the number of craters on the x-axis here on top. So you can see this kind of follows a logarithmic trend. The number of craters decreases as you get further back in time, much as you would expect. So the older ones are less well preserved. They've perhaps been eroded, or they've been recycled by tectonics. In some cases, perhaps buried. But it's not a very. There are a few quirks within this. So if you look here, and that's the box that's zoomed in here, you can see that it follows this kind of logarithmic trend, and then it reaches this point here, and then there's a step. And this is what's known as an impact cluster. So a series of impact events over a short period of time, perhaps a couple of million years, and in this case back in the Ordovician, where what happened in this particular case was that there was a breakup event. It's quite well established now. There was in the asteroid belt, there was a large asteroid that broke into pieces, and that sent a shower of asteroid fragments into the inner solar system that then collided over time with the Earth, with the Moon, with the inner rocky planets. So that's the only documented example of an impact cluster statistically above the average impact cratering rate in the geological record. Within that impact cluster is this peculiar doublet here. So this is the Lochne crater in Sweden, which is actually also a marine crater, one of the few. And the Malingen, I'm not totally sure I'm pronouncing the quirky Swedish A properly, but the much smaller Malingen crater to the southwest. And these are dated from the melt rocks within the craters. They're dated to precisely the same age. So this looks like it really is a case of an impact doublet. So two asteroids, perhaps a binary asteroid that comes into that collides with Earth, and the two individual asteroids separate and form their own craters. So very few marine impact craters, very few impact clusters, only one, and very few impact doublets or binary asteroid collision events. Which takes me on to, and keep that in the back of your mind as I go through this, because I'm going to propose at least that some of these conditions might be relevant here. Okay, that takes me to the subject of the talk tonight, which is the Nadir Crater, offshore West Africa. So the figure here, you see a map at the top showing the bathymetry, the depth of the seabed. So the area up here on the east is relatively shallow, about 100 meters, a couple hundred meters in the shelf. Then there's an area that's a little bit deeper, up to about 1 kilometer water depth, known as the Guinea Terrace. It's got kind of the continental crust beneath it has been extended and stretched a bit. And then the kind of deep water areas out beyond that. The lines here are seismic profiles, seismic reflection profiles. So for those of you who don't know, this is where you have so for each of these profiles, a ship has sailed along that profile with an air gun behind it, setting off seismic, providing a seismic source, so sending sound signals into the Earth, and they're reflecting back off boundaries in the subsurface. And that allows us to create these two-dimensional cross-sections through the Earth's crust there. So this cross-section here is from north to south, across the Guinea Terrace, the Guinea Plateau. And you can see you get a general idea of the geology. There's this is about 10 kilometers thick. This is in time, but this is roughly 10 kilometers thick stratigraphic sequence sitting above basement here, crystalline rocks down here. In the north, it's very flat lying, so not much going on structurally, not much complication, not much deformation, with the exception of this area in the north here where there are some salt diapirs, so salt rising to nearly the surface in some cases. And the very south here where there are some volcanoes of Paleogene age, right? So roughly 55 million years old. This is the Nadir seamount, of course, which provides its name to the crater that we document. So if I then go to show you another seismic section going from east to west, this time it goes through some exploration wells. That well is shown on the seismic profile here, so that's drilled to a couple of kilometers below the seabed. And from that well, we have microfossils that we can use to date the sediments, the stratigraphy. From there, so you can see the different ages that are signed here. This is, the blue is Jurassic, the green is Cretaceous, and the orange is Paleogene or tertiary, if you prefer the term. And the boundary between the Cretaceous and the Paleogene is shown by this yellow dashed line here. So what I'm going to show you next is a little zoom out of this little feature here, which looks very anonymous on this line, very subtle in this line. But this is the feature of interest. Oh, I should add as well, at the end of the Cretaceous period, the shelf edge is sitting here at this red star. So whatever is happening here is in water depths of several hundred meters at least, several hundred. I'll come back to the water depth later. Okay, so let's look at that in a little bit more detail. Right, so I'm going to show you the seismic at a little bit of a larger scale, then I'm going to zoom in and show it without any filters, without any annotation, so you can make a judgment for yourselves. Maybe I should have a vote. So again, this is the Cretaceous stratigraphy in green here. This, now note that the z-axis here is in depth, so this is depth on the going down, not two-way time. And you can see what the crater looks like. So we have this kind of concave up feature at the seabed, and sitting above this deformed layer below it, these deformed layers below it, which kind of dome upwards up to the crater floor. Either side of that concave up feature, we see this zone of extensional faulting mainly on either side. We're calling this damage zone. So just to zoom in now on that box, just in the central part of the crater with nothing shown in it, you can now see for yourself and make your own judgment. But again, what I see here is at the top Cretaceous, approximately the top Cretaceous, there's a little bit of uncertainty there. We can see again this concave up surface here. There are several packages within this. So there's this kind of slightly more transparent package at the base, and then a more stratified package sitting above it within this crater. That sequence sits above this heavily deformed sequence of sedimentary rocks just below the crater floor. And then you see this very deformed high amplitude package here from the Turonian to the Albian that's faulted locally in here and then folded significantly up to the crater floor. So just in terms of dimensions, to give you a little bit of a sense of perspective, that's about 8.5 kilometers on this seismic profile. If we then construct, if we kind of flatten that and assume that that was what the seabed looked like before this crater formed, the depth of that is about 200 meters at the deepest point. And the height of the uplift relative to the regional surface here is about 350 meters. Actually slightly more than that in the new data, but 350 on this line. And the moat on either side of that, so this collapsed area on either side of it is about 100 meters below its regional. On either side of the crater, so you see that the crater fill itself is quite transparent, quite low in amplitude. I should add that the seismic amplitude is a function of the amount of energy that's been reflected back to the surface. So the stronger the contrast in lithologies, the higher the amplitude. So on either side of the crater, you see this high amplitude sequence here. So there's something that's sitting around the crater that has quite a different density or different physical properties to what was in what's adjacent to it and what's above and below it. So to me, the first time I looked at this, I wasn't looking for craters. I was doing a project on tectonics and paleoceanography and other things. I looked at this and I thought, surely not. It looks a little bit like, some published craters that I'd seen. I wasn't a crater. I hesitate still to call myself a crater specialist. But it occurred to me that it looked a bit like some published examples of impact craters, particularly these complex craters, such as the one shown up here. But at that point, I only had one two-dimensional seismic profile across this, which is it's a lot to claim. To claim something like this from one line. So at that point, I managed to find another company that had some data here. So now this map here shows the location. That line I just showed you is this line, figure 2b. But you can see that there's another line here on the red survey, if you can see that, has a different orientation and has a tighter line spacing. So that in theory, we can constrain things a bit better with that survey. So the second line I'm going to show you is that second white line up here, cutting across the edge of this crater in a southwest to northeast orientation. So again here, you can see a central crater that's in this case about 8 kilometers in diameter, maybe a little less here actually, 6 kilometers or so. You can see the central uplift, although it's less well expressed, I think again because we're on the kind of edge of the uplift. And you can see this damage zone again on both sides. You can see the high amplitude facies extending on both sides of the crater, getting a bit dimmer away from the crater. Okay, this is really intriguing now. I've got two 2D seismic profiles. Also from the other profiles, you don't see the crater itself, but you can map out the damage zone, and the damage zone is circular, so it's something like 25 kilometers in diameter, and it's roughly circular. And the crater, you can't constrain it absolutely precisely, but it's at least consistent with a circular geometry. So that's interesting, very intriguing. So all of these observations start to kind of lend itself to this crater hypothesis. But at this point, I thought I better get some actual specialists into the room and into this discussion. So I got in touch with Sean Gulick and Veronica Bray from Texas and Arizona. And my colleague, co-author Sean said he gets like 10 of these emails every week. I found a crater. And actually, once I published this paper, I started getting 10 emails every week. It's kind of died off now, but he agreed to look at it, and he looked at it for 5 minutes. He said, "Yeah, that looks like a crater. That looks like an impact crater." So that's good. I got the expert on board. So there are a few things. So with Sean, we decided better do some QC of the dimensions, just to make sure that the geometries are what you expect, the dimensions are what you expect for an impact crater. This is a figure showing the height of the stratigraphic uplift on a log scale on the left-hand side, on the y-axis, and the diameter of the crater on the x-axis. And all the craters that are well constrained, so where we have good data, are plotted on here. And then there are a few trend lines shown on there. This figure is from this paper by Osinski et al. In 2022. And then if I plot Nadir on there, the crater, at this point, has got a name, the Nadir Crater. It sits right on that trend line here, 400 meters uplift. That 400 meters is slightly updated from data I'll show you a little bit later. And then the height of the diameter of the crater is 8.5 kilometers. So it fits right on that trend line. That's good. That's reassuring. And then if you plot any other ratios of, for example, the height of the rim to the depth of the crater, the width to the depth of the crater, the rim, the central part of the crater to the damage zone on either side, all of them are consistent with what we see for other impact craters, both on Earth and elsewhere in the solar system. So that brings us to this question. Like, all the geophysical evidence is consistent, at least with an impact origin, for a mid-size complex crater. But you have to kind of think of other alternative methods for generating this. So could it be anything else? So two obvious, or probably three obvious candidate processes that can make craters like this. One is salt dissolution, where salt sits at the surface and the salt dissolves out and it collapses in, the seabed collapses down. One is volcanism, some kind of volcanic crater. And the other one is something like a gas blowout or gas escape structure. So as I mentioned already, there are salt dissolution features in the very north of the plateau up here. If you look at the seabed in the present day, you can actually see craters here that are about 10 kilometers in diameter, so very similar in terms of scale. So these sitting above or adjacent to salt, it appears. So could it be salt? Well, there are a few reasons why we don't think that's the case. The morphology is very different. So salt collapse craters tend to, they occur because you dissolve away the salt below, and the seabed collapses in on top of that diapir. So for one thing, you need some evidence for salt. So in the north of the basin, there are big diapirs. You see them very easily on seismic. We don't see anything like that in the south of the plateau. So it's about 300 kilometers to the nearest salt body. And we don't see any of the other features that the features that we see in Nadir, you don't expect to find in salt withdrawal basins, or salt collapse craters. So we don't see, you wouldn't expect to see a rim, the ejecta-like feature that indicates that material has been thrown out of the crater. None of these things are present. So no evidence really for salt withdrawal or salt collapse. The other feature, I mean, superficially, this diagram on the left, the uppermost part of that looks a bit like, quite similar to an impact crater. This is a maar, or a volcanic crater that forms because of a so-called phreatomagmatic process where you inject magma into water-laden sediments. The magma reacts with the water, and that causes an explosive evaporation, essentially, of the water, and explosive ejection of material from the crater. So there you would get the ejecta on either side of it, potentially. The crater morphology looks superficially similar, and there are volcanic features around in the southern margin of the plateau. So when my concern, even by the time this was published, was that, well, what if it doesn't look like any of the other volcanic craters, but could it be? We acknowledge that in the paper to some degree. But these are, if it was a maar, it would be the largest one on Earth, for one thing, by a factor of 3. There's nothing larger than about 2 or 3 kilometers documented anywhere on Earth. And it just doesn't really look like, so you'd expect to see some other evidence of volcanic rocks nearby in the seismic. We don't see that. And the maar doesn't have this stratigraphic uplift, or the central uplift that we see in Nadir. So it really doesn't look like it is that. The main concern I had was that we do see other volcanic features some 50 kilometers to the south of it. They're a little bit younger, Paleocene in age, but that was the alternative, the main alternative, and still is the main alternative. I'm going to argue that we now can. I'll argue against that a bit more later on. So the last mechanism, potential mechanism, is that of gas escape. So if you've got a lot of shallow gas forming in the subsurface, it makes its way up to the surface, and at a certain point, it overcomes the fracture pressure of the shallow stratigraphy, and it explosively makes its way through to the surface, creating large pockmarks. So this is one of these pockmarks in New Zealand, with the city of Wellington shown inside it for some reason. Wellington is not in the bottom of a pockmark, but just for scale. Could it be something like that? Or could it be, this is a figure from a paper we published a few years ago showing these large crater-like features that are formed by currents in the ocean, so just currents winnowing away the seabed into these circular depressions. Well, again, you don't really see significant deformation structures in the subsurface with either of these. Sometimes gas escape structures form above mud volcanoes, but generally speaking, they're not consistent with what we see in the Guinea Plateau. And the other thing is they tend to come in clusters. So you don't very often get a single gas like pockmark on its own. Usually there are multiple pockmarks together that form a cluster. In the case of the crater that we have here, it's on its own. It's a standalone crater. So we don't think it's that. But to kind of, still we only have 2 seismic profiles, so can we replicate the geometry of the crater by modeling, by numerical modeling? So the figure I'm going to show here is a hydrocode model made by my co-author, Veronica Bray. So it's going to simulate an impact event of an asteroid. In this case, we're going to jump straight to the best model. We, of course, ran lots of different simulations, but this is an asteroid of about 400 meters diameter, hitting the seabed at 20 kilometers per second, which is quite standard for an asteroid impacting the surface. And it's at 90 degrees, just to simplify the model. The bit on the left of the model, which is currently blue, shows you total plastic strain, so just strain or deformation. So where this turns red is where we get the most strain. At the moment it's blue, and where it's blue there's no strain. And on the right is the stratigraphy. So here is mudstone or shale of several kilometers thickness. The gray here is that distinctive high amplitude package of shale, which is actually a black organic rich black shale, and it has slightly different physical properties. And the light brown is water. I didn't choose the color scheme. So the light brown is water, so keep that in your mind as I run the simulation here. So we're going to see what this looks like in terms of deformation. So once this starts, you can see initially this transient crater forming here, which is a couple of kilometers deep. And then the material in the subsurface flows vertically back up into the crater because of this process of acoustic fluidization. And then it freezes at a certain point. Once the shock energy decreases, it freezes in this morphology. You can also see these enormous tsunami waves, right? So it's about more than 2 kilometers above the top of our model. At the center, if we go a little bit further back in time to here roughly, so well over 2 kilometer high waves collapsing onto the surrounding sea. And at a certain point, the sea is completely evacuated from the crater floor, right? So the crater floor is, so that in this case, 800 meters of water has been evacuated completely, and then it cascades back into the crater at this point in time, obviously quite violently. So that gives you a sense of what happens in terms of what the water masses and the rock, but it also gives you the geometry of the crater, and it's a relatively good match for what we see in seismic. So if I show you a number of different simulations, or the outcomes of a number of different simulations now with the water removed to make it clearer, the very shallow ones don't really look convincingly like what we see because the uplift is too high. It's come up. A lot of that material is ejected, and there's too much material removed there. The very deep ones, the deep water ones, 1,500 meters in this case, the deformation is too simple, and the central peak is too high, so it doesn't really look like what we have. So the best match for what we see is essentially this 800 meter model here. And we ran it in 300 meter increments, could probably be improved a little bit. But that's the best match that we have. But that's also consistent with what we think from seismic. So I mentioned that the shelf edge is here. The shelf edge is probably 100 or 200 meters water depth already. And then it's another few hundred meters at least onto the terrace. It's currently at about 900 meters, so we don't expect it to have been much deeper at the end of the Cretaceous period. So that is the evidence so far published for an impact origin from both seismic observations and modeling. But what I want to do for the next few minutes is to talk about the consequences, the environmental consequences of an impact of this size, just to give you a kind of sense of what this would look like. So a 400-meter asteroid is approximately the same as this image here. This is the Bennu asteroid, which is considered to be the most hazardous object in the solar system. It has a Palermo scale rating of 1.42, which I've discovered is rather high. So this has, so it's the highest hazard rating of any object in the solar system. It has a 1 in 1,750 chance of colliding with Earth in the next couple of centuries. And if you're around, I think it's the 24th of September, 2182, it has that day, it has the highest chance of at any point of colliding with Earth. So watch it, pass a message on to your great-grandchildren. This was recently sampled actually by NASA. NASA have just taken a sample back to Earth, and there's now lots of research going on this pristine asteroid sample. Another reference point, if you remember the Didymos asteroid that was the subject of this recent NASA DART mission, where they flew a small satellite or something into an asteroid to see if they could knock it off course. So that was the directional asteroid, some direct asteroid redirection test or something. I can't remember what exactly it stands for. So it's kind of similar in size to that. Actually, the one that they knocked off course is the smaller of Didymos is a binary asteroid. So they targeted the smaller of the two. I think it's not the 765 meter one. But that gives you an idea of something that plausibly could happen in the next century. What are the consequences of something like this? So if you're standing at 50 kilometers distance, so imagine this happens 50 kilometers out into the North Sea from here, what do you see in Edinburgh? So standing in Edinburgh, you would see the fireball radius would be about 5 kilometers in diameter, so you would see something that's about 24 times brighter than the sun on impact. This image here is from the Apache nuclear test. It's a 2 megaton explosion that's carried out in 1956 in the US somewhere. So this is about 250 times the energy of that Apache nuclear test, so 250 times as bright as the image you see there. In terms of the air blast, this is where it gets really dangerous because the fireball wouldn't do anything, but the air blast would. So again, in Edinburgh, 50 kilometers away, most buildings would collapse. Maybe not some of the strong buildings in the new town or here in this part of the city, but glass shattering, 90% of trees blown down. And to give you a set, that air blast will arrive after 3 minutes, and that air blast is what does a lot of the damage actually. That energy would be about 1,000 times larger than the recent Tonga Hunga Ha'ai Pai eruption, 2022. This is a very famous eruption. That image shows a satellite image of that eruption. And if you remember, those sound waves traveled around the world several times. You could see the pressure waves traveling around the world. In terms of an earthquake, that would be about this distance would be about the equivalent of magnitude 6.7 earthquake. So quite a damaging earthquake, depending on whether your infrastructure is set up for that or not. Obviously, that depends on the building types. Earthquakes don't kill people; buildings do. The old adage. But it might also could also trigger underwater landslides, which I'll mention again in the next slide. The other aspect of this is for marine impact, unique to marine impacts are the tsunamis. And you already saw the tsunami model, the waves propagating away from the impact. So there we have 2 kilometer waves immediately after the impact, but they're quite short. They collapse in on the seabed. They're essentially part of the ejecta curtain, part of this curtain of material that's ejected from the crater. But still, by the time you'd reach, let's say, 50 kilometers from, again, here in Edinburgh, to keep that analog, you'd have a tsunami wave height of about 500 meters. For the case of Nadir, which is in the middle of the Atlantic, it's a transocean tsunami, so the model suggests that you would still have a 5-meter tsunami by the time you reach South America. So it's not just a localized effect. And then the really interesting feature of the Tonga eruption was that the tsunami, from this eruption generated tsunami, was that the tsunami waves were in resonance with the atmospheric pressure waves, and those amplified the tsunami waves right across the world. Actually, even in the Atlantic Ocean, there were tsunamis recorded, and there's no direct ocean connection. So, there are processes going on that you don't, until you have an event like this, you don't understand what the additional, how processes cascade or interact. Another element to this, I mentioned already that there are black shales here. So this gray layer here consists of black shales. So what would happen to that material if it's vaporized. So in the case of Chicxulub, which is the big event, a lot of salt was vaporized and other material vaporized to make sulfates in the atmosphere. There were a lot of particulates, a lot of aerosols that got into the atmosphere. And those combination of particles that were sitting in the atmosphere led to a global cooling event of about 25 degrees Celsius. So an instant global cooling of 25 degrees Celsius. That's what was primarily responsible for the extinction, or at least contributed significantly to it. For Nadir, target stratigraphy consists of black shale. Remember, Nadir is a lot smaller, so we'll come back to that later. But the target stratigraphy is very different. And actually, it turns out that the material that you vaporize has a very important influence on the environmental effects. So in this case, you would likely generate instantaneous methane of an unsubstantiated quantity. We haven't done any calculations in this. So this might actually have the opposite effect of a mild warming effect. And then there are other feedbacks and cascading processes I mentioned. Maybe there's evidence for submarine landslides at the edge of the plateau on the far west there. So there could be, there could be methane released from that as well. That's been proposed for other impact events. So this figure here just kind of summarizes that impact. 20 kilometer per second impact under the seabed generates this large fireball, propagating transient crater forms. Shock pressures propagate away from the crater. These turn into pressure waves and generate earthquakes with increasing distance. Then after about 30 seconds, the material flows back vertically up into the crater, forming this complex crater morphology, and then everything collapses in around that deforming crater. And the water resurges back into the crater. Okay. The final thing I wanted to mention was the potential, the intriguing potential relationship with Chicxulub. So we're 66 million years ago. We already know that there's a large impact crater here. There's Chicxulub. Chicxulub occurs once. So the figure here, I should mention, the y-axis here is the number of events per year. So this is 10 to the minus 8. So that's 1 per 100 million year event for Chicxulub. Something the size of Baltish, I'll come back to Baltish in a second, but Baltish occurs at a very similar time, about 65 million years ago, 65.4. Would expect to occur about once every 3 million years or so, 10 to the minus 6, or I think 3 to the minus 6. And something the size of Nadir would be estimated to occur about once every 700,000 years. Right, so those are the frequencies. So one thing, I mean, it could just be a coincidence. You have 3 events side by side, co-located in time. And I haven't really done any rigorous statistical analysis to test, and I'm struggling to know how to figure out how to do this, because the other element to this is that we only have we only preserve about 2% of craters. So and the preservation potential depends on the size. So I'm trying to figure out how to kind of put a number on this. But it's intriguing that we have 3 large craters formed within a short period of time, and 2 of them are very large, right? So Nadir is by far the smallest of the 3. Hypothesis 2 is the impact cluster hypothesis, or the little cousin hypothesis. So that is that, much like in the Ordovician period, as I already mentioned, that there was perhaps a breakup event in the asteroid belt, a flux of material coming into the inner solar system, and we had 1, 2, 3 impacts at least in a short period of time within 1 million years. Perhaps others. There are, I should add, Karina? Yeah, I was briefly talking to at the beginning of the session. There is another proposed impact crater of a similar age sitting in the middle of the Amazon rainforest, which is intriguing. We don't know exactly what the age is, but approximately at the top of the Cretaceous period. So how to test this? You would really need, to begin with, much better age constraints for Nadir. We have very good age constraints for Baltish and Chicxulub, of course, but it would be intriguing to get samples from Nadir to see what precisely the age is, but also from the other event, I've forgotten the name, in the Amazon. The third hypothesis, if many of you will remember the 1994 Schumacher-Levy comet. So this was a comet that disintegrated as it passed nearby Jupiter back in 1993, I think. Disintegrated into many fragments, and then in 1994, those fragments collided with Jupiter one after another over a period of about 9 days. I think 17 Jovian days. Jovian days are slightly shorter than ours. So, you know, that means that the craters are very widely distributed spatially, but very close together in time, within days. So to test that something similar could have happened in the case of Nadir, so i.e. an asteroid is passing close to Earth, but disintegrates, and then the dispersed fragments then collide on a subsequent pass. You'd have to test and see whether the dates really correspond to the year, which is, of course, difficult to do, but they have an extremely good chronology for Chicxulub, for example, but you'd need to get into the crater fill to do that. The tantalizing prospect that these might have been connected, of course, led to quite a lot of media interest. So this is a New Scientist article. A second asteroid might have struck Earth when the dinosaurs died, or that the crater might be the baby cousin. New York Times, relatively nuanced, all very much focused on the dinosaur hook, but relatively nuanced, I think. Descriptive one there. The Sun, of course, likes to make things a bit more exciting. And, you know, it's great to be honored with the term of a Scots boffin. I think I was the only Scot on the author list, but appreciate that. And then there are a couple that are a little bit more subtly not quite what we're saying, because these suggest that a second asteroid likely led to the dinosaur extinction, or not one but two asteroids might have slain the dinosaurs. Are we proposing that the Nadir crater actually led to that extinction event? Well, not really. If we look at the metrics of the two impact events, so the diameter, Chicxulub is a lot larger. It's about 30 times larger in diameter than Nadir. The crater is much larger than Nadir. If you look at the energy involved, we have 5 orders of magnitude difference in energy released by the Chicxulub event as compared to something Nadir-sized or Bennu-sized. The earthquake, remember that the moment magnitude scale, each point in that scale is 30 times larger than the last one. So we have, again, 5 orders of moment magnitude difference in scale and the size of the earthquake. A size 11 to 12 earthquakes are very, very difficult to imagine. The largest ever recorded is 9.5. So we're talking here about something 1,000 times larger than the largest ever earthquake experience in human history for Chicxulub. And also the amount of material vaporized, for example, would be a lot larger. So likely dwarfed by Chicxulub, unless perhaps there were a cluster of other events. So I'll leave that hanging. Final thing I just wanted to leave you with is the next steps. What are we going to do with this project going forward? So I mentioned already that I have a drilling proposal, I think I mentioned. So this is the JOIDES Resolution, which is the kind of flagship drill ship of the International Ocean Discovery Program. So I've submitted a proposal a couple of years ago now to go and drill this crater. So 900 meters of water, 300 meters of sediment, and then another few hundred meters below the crater floor. Unfortunately, that drill ship has just been decommissioned, and IODP have announced that they're no longer going to run this drill ship. The program is changing. So I've resubmitted this proposal to drill it with a geotechnical drill ship that has slightly more limited drilling capabilities and doesn't have the same lab on board, but would still recover the core. And then at the moment, we're just working on we're finishing up a project that's sponsored by NERC, the Natural Environment Research Council, because we got access to a new 3D seismic data set across the crater that we have just submitted a paper now in review with Science Advances. So I'm going to give you a sneak preview. I'm not allowed to show much of this yet, but I will give. I am allowed to show this video of the crater. So what I'm going to show here on this new 3D data is a 3D kind of oblique view looking north. This is the seabed, and these are two seismic profiles, kind of an east to west profile and north-south profile. Not quite, but more or less. So I'm going to strip off. I've interpreted the data. I'm going to strip off the interpreted layers one by one, so you can see the crater morphology. So yeah, as I mentioned, this is the seabed, so we're at 900 meters water here. If I strip off the tertiary or the Paleogene, this is what the crater looks like. So now you can really see the geometry. It's nearly circular, slightly polygonal on one side. There are reasons for that. If I strip off another layer, we get, this is the shallow deformed subsurface. You can see these incredible deformation patterns, concentric patterns nearby, and these polygonal patterns further afield. We go down deeper. We're now about 300 meters below the crater floor. You see this, now 600 meters, the video's too fast. You can see this moat here, the central uplift, nicely preserved in the middle. I think the video stops there, so I don't need to pause it. And then at the very end here, we can see the deepest mapped layer. You can see beautifully expressed this moat. We can see these faults here are inherited structures. These are deeper structures that are exposed in the that are kind of expressed to this shallower layer. But you can see the central uplift. You also see these ridges on either side of it, which we are claiming we can use to reconstruct the angle of impact. So we think that this impact came from this direction here to this direction here. So from kind of east to west, northeast to southwest. I think it's actually more or less east to west, if I remember well. For more information on that, you have to, in a few month or two, maybe. It's been in review for a while. Look out for this new paper that's hopefully coming out soon. In this paper, we're also claiming that the seismic data, for the first time, nobody's ever claimed this before, but the seismic data, if it's this good and this clear, is sufficient on its own to actually conclusively state that this is an impact structure. We don't necessarily need shock minerals to prove it. So, with that, I'll leave you this cartoon. The credit to the cartoon on the right-hand side there. I can't actually read it. So please, yeah, thank you for your attention, and please let me know if you have any questions.